Sure. So let's start with what today's agenda. Like what I'll be covering today is what are large language models, what is tokenization process in the large language model, what is vectorization, what is attention mechanism, what are transformers at a very high level, what is self-supervised learning, fine-tuning, RAG, retrieval-augmented generation, agents, and model context protocol. So I have designed this course in such a way, like you get a hang of it, like AI will no longer be a black box for you. You can understand, like most of the companies today, what they are doing is they are implementing agents, right? Or when you work on your company, you will be implementing agents. So when something breaks in production, right? If you just know at a surface level, you'll not be able to debug it. Or like if your team is implementing something, you'll not be able to guide them to how debug the solution or what is the concept actually going behind it. AI will always be a black box for you. So if you learn these concepts of AI, right? AI will no longer be a black box. You will develop a core intuition of how like this chat GPT like interfaces, Gemini, and all these things are working, right? So it's a mix of combination plus it's a combination of theory and practical, where like the first seven concepts, right? They are basically like mostly theoretical, but they are very essential in order to understand the last three concepts, which is like RAG, agents, and MCP. So I hope like if you go through articles or anything else on the internet, right? These are like I mean top 10 concepts of AI that surface up at every level. Like whether you are reading a paper, you are reading any article. So everywhere these 10 concepts are mostly used, right? And I would like to just also start with this quote. I really like this quote, which is like machine intelligence is the last invention that humanity will ever need to make. This is by Nick Boras. So yeah, it was pretty good. I like it, so I like quoting it. Okay, let's get started with our first concept. So the first thing is like I'm sure almost all of you might be interacting with GPT-4, Claude, Gemini, and Llama, right? So what are basically all of this? Like you know Chat GPT, but in the ML world, what are they called? They are called as large language models. So you will see this term used very interchangeably, like GPT and large language models. So basically these terms like GPT, Claude, they in the ML world, they are called as large language models. So why the term large, right? Because they are trained on the data of the internet, like petabytes, millions of data, almost all the articles which are present on the internet. They are trained on they are trained on that, and they have millions of parameters which are fine-tuned while they are training. So the term large comes from the meaning that they have a huge training set and they have a large number of parameters which are fine-tuned, right? So now how they are different from traditional programming, right? So what traditional programs do is like if you want to like search for something, like you store it in a database, you retrieve it, right? We write programs like that. And basically data is stored anywhere and we try to retrieve it, right? And there are a bunch of if and else conditions, right? But these large language models are basically different from like traditional programming. They don't do any memorization, or like they don't have an if else condition that if I see this data, I will give this output. If I see this data, I give that output, right? So they are not that. They are based on like pure maths and statistics, right? Now, what do actually ChatGPT or these large language models do? So basically, what they do is when you type in a question, right? For example, the sky is, like, so what the only work that this chat GPT does is they want to predict the next word that comes after it. So it's very astonishing or like very strange when you like see the experience, right? When you type in, when you go to chat GPT and type something, right, you get a bunch of like a big answer or something like that. So it's hard to imagine that the only thing that they are doing sequentially is like predicting the next word after your question. So let's take an example. So let's say if you type in the sky is, right? So what it will do is it will just predict that after the word the sky is, what should be there. So it will predict blue. Okay. Then it will take the word blue and then it will predict what should come after the sky is blue. So it will predict because. Now it will take this whole thing as an input, the sky is blue because, and then it will predict this next word off. Similarly, so forth and so on until it gives you the answer. The sky is blue because of the scattering of sunlight in the atmosphere. So it's just taking your input question, adding one word at predicting the next word, one word at a time, taking that as an input and predicting the next word. Okay. So this is what it is doing at a very high level. Okay. Now, how do they do it? Right. So I said that they are trained on a large corpus of data. but and they are mathematical systems, right? So so when I type in the sky is blue, how is it predicting it that when I type in the sky is, right? So how is it predicting that it's blue, right? So what is happening is, let's say on the internet there are millions of articles, and those articles contain this particular information. The sky is blue. So this is the training data. On a clear sky, on a clear day, the sky is blue. When I look up the sky, it is blue. The grass is green and the sky is blue. So all the articles on the internet have this information about sky. So now when I type in the sky is, obviously the probability of the word blue coming after sky is 100%, because in all the articles it has seen so far, it sees that blue is followed by sky. So when you type in the sky is, so it just types in, it gives you an answer. It predicts the next word, which is blue. So see, it has never looked at the sky, and it's not an intelligent system that knows that sky is blue. So here it's a probability based prediction, right? So let's say if in the internet there, if I add one more word, right? I change all the articles on the internet. So this is just an hypothetical situation which I want to tell you so that you understand the context. So if I change all the articles on the internet and rename it somehow, the sky is yellow, right? So the model, the very next day after it's trained on that data, it will start saying that the sky is yellow. So do you see over here that it does not have any inbuilt intelligence or something? It's just a system which is working on probability and statistics, right? So now if I add one more sentence in the training data, at night the sky is dark, right? And now if you ask the sky is, so now the probability changes, like 80% probability would be blue and 20% probability will be dark. So how it answers now how it will answer this question, we'll take it later. Okay. So this was the first concept. So what are large language models or ChatGPT? What are they doing at the very core level? So this was the concept related to do. I will take a pause over here and ask, like, if you guys have any questions on this particular topic. Like, I'm just trying to build it, build the intuition. We'll build the intuition slowly, but any questions on this particular thing? Shirisha, your voice is a little low. Can you be a little louder? Okay. And I could not hear you. So anyways, we can connect at last if you have any questions. Okay. So the next, let's move on to the next term, right? So the next term is tokenization. This is also very important, right? Whenever you learn about this chat GPT, or if you read any article on the internet, or if you see your colleagues in office talking about this chat GPT or any models, right? You'll frequently hear these terms: input token, output tokens, context window, time to first token, right? So what are these basically? So these are basically, these are concepts related to tokenization. So basically computers cannot read words. We know that, right? They don't understand human language like English, right? They do math, they do binary, but they don't understand English, right? But we actually understand English, and ChatGPT is giving you answers in English, right? So we need to somehow translate what the computer understands, which is like math, like our general language, to math, right? So tokenization is the process of converting words into number, right? Okay. So what happens during tokenization is the model breaks your input into tokens. Like, let's say if you type in a word, the sky is blue, it will take each individual word and convert it into a token, right? Or a number, basically a number, right? We'll see this in detail. So basically, like I took an example, the sky is blue, right? So the tokenization process will happen on this. They will be broken down into individual words, and then they will be assigned a number. Okay. Now the computer can understand numbers, right? It does not understand English, but it understands these numbers, right? So this is what tokenization is. Why I'm explaining this term is, like, if you are a manager, right? Let's say for an example, you will hear a lot, like if your team is working on a model, right? They say that we need this particular model to work on this particular thing. So the pricing of the model and everything all are based on tokens, right? So in order to take a decision that whether I should take this model or use this particular model, you need to understand what tokenization is at the core. Now, there are different ways by which you can tokenize. First is like character level tokenization. What you basically do in that is you take each character from this particular sentence and convert that into a number, right? So that is character level tokenization, but it's not used anywhere, right? Second is word tokenization, which is like the example that I explained. Your sentence will be taken, broken down into words, and then assigned a particular number. So this is used at many places, but the actual algorithm that a GPT, Gemini, all these things use is subword tokenization. They use an algorithm called byte pair encoding. So in today's demo, I'm not including this, but we will look into this further if we join the course, right? And like I said, like when you type in sentences into chat GPT, right, they are called input tokens that the model is taking into account. So your chat is converted into a your whatever you type in your question, right, that is converted into numbers and that is passed as input tokens. Whatever the model gives you the answer, that is called output tokens, right? And there is another interesting term which is used everywhere, which is like context window. So context window is input token plus your output token. So the model can at any point of time hold only a certain number of tokens, right? Which is a combination of input plus output token. You will hear this a lot of time. Like previously, if you might have worked on ChatGPT, you might or you might have used ChatGPT. It used to like take only like a few paragraphs as input and then put answer only based on that, and it used to give limited set of output. Nowadays, as the models are growing, you can pass in your whole code base as input, right? So basically, what has increased in the model is their context window. So, and like context window is nothing but input tokens plus output tokens. So this was tokenization. So we have till now learned two concepts: what are LLMs, and how are words or the questions that we type in into GPT, right? How are they converted into mathematical form via tokens, right? Via this tokenization. So we learned tokenization, right? Now let's move on to the next concept, right? So here, if we see, what we have done is we have taken these particular words and assigned them certain numbers, right? But sky has a meaning, right? Blue is a color, is something which is meaningful in the real world. By just assigning the number, how will it understand what all of this is? Like, what is sky? What is blue? The matter. I mean, we just assign some numbers randomly. How does it capture the context or the meaning of the word, right? So there is where this vectorization or embeddings come into picture, right? So what is vectorization or embeddings? This is also a very common term. Like when you start working on any of the AI applications, you will hear about vector DB, vectorization, and stuff like that. So what is vectorization? Vectorization in machine learning and AI is the process of converting your raw data such as text, images, audio into numerical vectors, right? So we converted them into so first, through tokenization, we converted them into numbers, but numbers don't tell us anything, right? So now we'll convert these numbers into vectors. So now we'll go back. So what are basically vectors? I will give you an inclusion for it, right? So if you go back to the 10 class math, right? So if I had to represent a point in a two-dimensional space, right? What would I basically do is, like, if I have this point, right, I will go along the x-axis, see it's 5, go along the y-axis, it's 3, and call it 5.3. This is how a vector is represented in a two-dimensional space, right? So similarly, like let's say if I add one more axis, which is the z-axis, it will be 5, 3, 2. So this is again another vector, right? That it represents. Now in the modern LLM or in the machine learning world, right? They Yeah, Sneha, you had any question? Okay, I'll continue. So in the LLM or in the machine learning world, right, there are no X, Y, or Z axes. We have something as like different kind of axes which represent real world concepts. Like height can be an axis, right? Then emotion can be another axis. Then formality, action, religious meaning, all these are different axes which are present in like LLMs, right? So why, I mean, it's very hard to understand like what do these accesses mean, or like why does it even matter? So what we are basically doing right now, right, to get an intuition is we have words, we are converting them into numbers, and then those numbers should also contain some meaning, right? So if it's a mathematical term, we use 1, 2, 3, 4, and then we can represent it, right? But since we have English words and we want to derive any meaning out of it, we need to use accesses which are different. So these kind of accesses are taken in case of LLMs. I'll give you one more example so that it becomes very intuitive. So let's say if we want to vectorize or represent a T in a vector space, right? So how would we represent it? We cannot represent it in terms of X, Y, Z and axis, right? Because they are numerical terms, right? So what will be the accesses in terms of the word T, right? So is it a beverage or not? Is it sweet or not? Is it hot or not? What is the Indian context? What is is it a formal thing or not? So these kind of abstract things will be accesses when we want to convert T into a vector, right? So the final vector for T, if I have to represent T in a multi-dimensional space, this will be the vector which will be represented. Yeah. So another example, and don't worry if these concepts are looking very abstract to you, or like you feel, okay, what am I talking about? These are common concepts in the machine learning or in the AI space, right? So you need to get a hang of it because we are kind of dealing between conversion of numbers and words, right? So another example, if I had to create a vector for coffee, right? So I will use the same feature sets, like beverage, sweetness, hot, Indian context. But chai and coffee, how are they different in terms of sweetness, in terms of hotness, on how they are served, and in Indian context, maybe coffee has a more foreign context. So the vector, if will the vector term created will be the vector for coffee will be created like this, and these numbers will represent these values. So these are the axes basically. Okay. And in real world, these accesses or these numbers are not hard coded, or nobody has created it. These are also created using some machine learning, using some models. One such example is text embedding ADA. Like you will also hear these terms a lot, right? So now I want to focus on one more part, like why are we converting these words into numbers and then vectors, right? So there are two main reasons for doing it. First one is like basically we are gathering some semantic context. Like we saw, right? When I'm creating the vector of T, I am adding some semantic context over there, that in terms of beverageness, what it is, in terms of hot, what is the value that it has, in terms of like sweetness, what is the value it has. So we are encoding some semantic meaning on that particular thing. And the other thing which is also very relevant to vectors is vectors of apple, like vectors of fruits, they will be very close together in the vector space, right? Similarly, vector of vehicles will be very close in the vector space. And similarly, vectors of animals will be very close in the vector space, right? So this is one property of vectors. So we find out cosine similarity between vectors and do some vector maths to predict the next sentence. Now we have converted each of the words into basically mathematical numbers, right? Vectors. So now we can do mathematical operations on them, like add vectors, subtract vectors, measure distance, compare angles, stuff like that. But the interesting part over here is how will it help us, right? So for an example, if I have to give an example, right? So what will happen is, like if you have an input sentence, right? So in your input sentence, we will do some math to figure out what should the next word be predicted. Like if the like king minus man plus woman, the vectors, if we do addition of this, it will automatically give you queen. Okay. Similarly for Paris, if you do Paris minus France plus Italy, it will automatically give you Rome. If you take the vector of Microsoft and minus the vector of Bill Gates from it, and add Apple from it and add Apple to it, it will automatically give you Steve Jobs. So this is the beauty of vectors. Like I'll take a pause over here and see if you can appreciate this matter, because it's like really beautiful over here. How we have taken words, converted them into numbers, then converted them into vectors, and now we are doing some math, and the meaning we are getting from there is like amazing, right? So this is like very amazing math. It will take some time to sink in, but just wanted to explain the concept of vectors as well. This is a very good link where which you can, if you cannot visualize right now, this is like a very good link where if you go in, right, it explains the vector math, like what happens if you do king minus man plus woman, right? So this particular thing over here. So if you see, if you do this math, the vectors that will be suggested is queen, then princess, and all those stuff. So this kind of math is possible on vectors, which makes it like really very interesting. Now coming back, so till now, what we have done is we have understood LLM, we have understood tokenization, we have understood vectorization, and like I said, don't worry. As you guys start working on any AI project, these terms will start growing up, and they will appear. Hopefully, they will not appear as an buzzwords for you. You will have some meaning out of them. Yeah.
Is there any tool that helps us to identify the vectorization?
Yeah, I mean, there is, like I said, right, there are algorithms which basically convert the words into vectors. So like word to vec is a particular algorithm which will take your input word and convert it into a vector. Uh, Swati, I'm not sure if that answers your question, if that was.
Yeah, yeah, I got it.
Okay, sure. So now we'll move to attention, right? So attention is also now, I mean, we have taken a sentence, we have converted it into a numerical form, we have gathered the semantic meaning of the sentence, right? But there's one more thing which is like very important. Like if you see, look at these two particular words that I'm sharing on my screen. I deposited money at the bank and I sat by the river bank, right? So what does the word bank mean in in the context of this sentence, right? It means it's talking about a financial institution, right? I sat by the river bank. It means it's a water body, right? So we as humans can find out what bank means by reading the previous context, right? Previous context of the sentences. We can understand what bank actually means, right? In this particular situation, it's a financial institution, and this particular thing, it's a water body, right? But when we are, so let's say what I said in the initial phase was like when you are predicting the output of a sentence, right? That is what LLMs do, right? So you need to consider everything, right? English is a tricky language. One word has different meanings as well. So how will machines understand that what does bank mean in this context? What does bank mean in this particular context, right? So that is where attention comes in, right? Machines also follow the same thing, right? Like we humans solve this problem by looking at the words which have come previous to these words, right? By reading at this, they can understand that bank is a financial institution. Like if I take another example, Apple released a new phone, right? Was a she picked an apple from the tree? The word apple is the same, but in this context, it means in the context of first sentence, it means the Apple phone, and in the second context, it means the fruit apple, right? So how do we make the machine understand that they are two different concepts over here? So that is what attention is, a mechanism that enables models to weigh the importance of different words in a sequence when processing data. So through attention mechanism or the algorithm, the machine can identify which bank are we talking about here and which bank are we talking about here. Let's take one more example, right? So if I have a sentence, just give me 1 minute. I think my pencil is somehow not working. Okay, never mind. I don't want. Okay, never mind. I'll just explain it this way. So we were talking about attention, right? So now let's say if you have a word which is called Apple's revenue. So what does that mean? Apple's revenue. Basically, it's we can infer, right, that it's talking about the Apple company, right? And if I talk about tasty apple, right? What does it mean? It's talking about the apple, a fruit, apple as a fruit, right? So now what attention does is, like, let's say if you have a vector of apple, which I have represented in this particular diagram, and you add the vector of revenue to it, it will push it towards the vector of companies with the vector which has Apple, Samsung, Meta as companies present, right? So this attention mechanism is the way through which it will do some math on these particular two vectors and push it towards the Apple company vector, right? Similarly, if I take the vector of apple, which will be the same as the vector of this, but the corresponding word like tasty apple, right? So this will push the vector of apple towards the vector of fruits, which might have other fruits like banana, mango, and everything. So attention is the mechanism by which we do some vector maths, and it helps us to predict like what is the meaning of the input sentence so that it can predict the output, right? So Apple's revenue, now if I have to predict the next word, I know that Apple revenue means the Apple company. So I look in this particular vector space and predict the next word from there. Vector apple plus taste, apple tasty. I know that I'm talking about fruit, so I'll predict the next word from this particular space. So this is what attention is all about. This was a major breakthrough because of attention, right? Google identified that this particular attention is the mechanism by which we can look at the surrounding context of any word and define inherent meaning from it. And that is how we can predict the next sentences. So that is the concept of attention. Now moving on to the next concept, which is transformers. So everything that we have learned so far, uh, like clubs into or working together forms a transformer. So these individual concepts that we talked about, like breaking the input sentence into tokenization, then doing embeddings on it, then applying some positional embeddings, and then passing all this to a neural network, and then getting the next output sentence. So all of this, the separate algorithms, when they work together, that concept is called as a transformer. So basically, the models that we work on, right, they are nothing but transformers. So it's very confusing. Like, I mean, to distinguish between, like, people get confused between what is a transformer and what is an LLM. So the transformer is kind of an architecture, and LLM is a trained model using that architecture. So every LLM is built on a transformer, but not every transformer is an LLM. So this is also terms which are very confusion. So basically, transformer is the architecture, and LLM is a model using that particular architecture. And what does a transformer basically do? It takes an input question and it, based on the training data, it just gives you the probability of the next output word. So that is what I explained you on a high level, what is LLM. Now moving on to the next concept, which is self-supervised learning. This is also a very, I mean, this is a very important concept in terms of machine learning. LLMs were possible because Google invented this self-supervised learning, right? So what in previous ML examples in ML world before LLMs came into picture, there was a problem, right? Let's say if you like the core idea of machine learning was if you want AI to recognize cats, right? What you would have to do is you would show it 100 pictures of cats and a human will label it that this picture is of a cat and this picture is of a dog, and then the AI will learn to say that this is a cat or a dog, but a human labeling is required, right? A human will go prepare a data set with like 100 photos of cats and dog, and then the machine will come in, look at those photos and make prediction, right? So this is a problematic area, right? Like I said, LLMs are trained on the whole internet, right? So to train the LLM, I cannot go and label all the data on the internet, right? It's not possible. So that is when Google came up with this concept of self-supervised learning, right? What does it mean is like you give so let's take an example of a sentence from the internet, right? So what will happen is you will take this whole sentence, the cat sat on the mat, and give it to the model to train on it. But what the model will do is it will mask the last part of it, like it will mask mat and then say that okay, I don't know what is coming next, I need to predict the last word of it. Okay, so the cat sat on the, it will mask this particular mat and then it will make a prediction on it. Initially it will give wrong predictions that cat sat on a dog, cat sat on the river, cat sat on a bank, all this, like, but eventually when it will be slowly trained, right, it will start giving you the right answer, the cat sat on a mat. So self-supervised learning is a way through which you can basically the machine can create the data on its own through which it learns. So this is also a very, I mean, it's these concepts which I'm talking about, right? They are basically hard to grasp at one go, but I think eventually, if you read more about it slowly and slowly, when you come into this machine learning and AI, these will slowly start making sense. Right now, don't be overwhelmed that I'm not getting a hang of it. When I also started, it was difficult to even imagine what is going on over here or how does it make sense. Okay, but gradually when you read about this space, it will start making sense. Now, one more difficult term, and then after this, things will get easy. So, what is fine tuning, right? So, like I said, right, that we train the LLMs on all of the internet, right? Everything which is present on the internet. So, what we do is when we have all these data sets, right? We after training it on the data sets or present in the internet, we get a base model. Okay. Now, the base model, what it can do is like it can fill in that blanks, which I told you in the beginning. But if we go to ChatGPT today, right, you give in a question and gives you an answer, right? So it's not kind of a fill in the blanks kind of things, right? So what fine tuning means is taking a base model and training it based on you train the model that you have to answer in the format of a question and an answer. That is one aspect of fine tuning. The other aspect of fine tuning is like I take a base model and what I do is like let's say if your company is into databases, then I train it on the material of fine tune it on the database material so that it can answer questions which are related to database very easily. So let me take an example from the real world, right? So what happens? What does fine tuning means, right? So let's say somebody is a doctor, right? So they learn like basic doctor and they are a general physician, right? So they have all the skills and everything. Now, if you ask them to do a heart surgery, right? You can't expect them to do a heart surgery because they are a general physician. They need to acquire that particular skill to do the heart surgery, right? To become a heart surgeon. Similarly, is the case of fine tuning. So a basic physician might have to read some more data or learn some more in the terms of medical terms to become a surgeon, right? So similarly, if we want models which can answer our company specific data, we need to fine tune it. We need to take the base model and basically train it on our company data, and then it will be fine tuned to answer your data. So that is what fine tuning is. And there are techniques like LoRa and QLoRa, which are used. They are again like related to machine learning, which are used to fine tune models. So this is what fine tuning is. Okay. Okay, I'll take a break over here and see. Those were quite heavy concepts. Is there any question around that, or is it even making sense? If If you guys can give a thumbs up and let me know at least that if it's making sense or not. Oh, okay. Okay, at least it's making sense to Swati, I can see. Thanks. So we'll move to the next concept, which is RAG. RAG is also like like when your company starts implementing or using AI, the first term you will hear is RAG. What is retrieval augmented generation, right? So now we know that how an LLM is trained, right? It's trained on the data of the internet, right? Whatever is present, easily accessible on Google, the articles which are present, or any website which have no restrictions, right? So the LLM is trained on that. Now, let's say if your company is building a chatbot, right? So your company has some documents which are specific to you, like Confluence articles and everything else, right? So they are very restricted. So the LLMs like ChatGPT and all, they don't have access to read those particular articles, right? Now your company has built a support bot wherein it wants to answer user questions based on the data that is provided by your company. So now LLMs don't have that data. So how do we extend LLMs? So that is what is called retrieval augmented generation, wherein what you do is like you take some additional, you take the documents which are related to your particular company, you do the vectorization which I talked about earlier, and store it in a vector database, right? So you store it in a vector database. Now, when your company employee is asking a question to the LLM, right, what it will do is before answering it back, it will go and check that particular vector database that, hey, it will go and check that particular database that, hey, do I have this information in the database or not? If yes, retrieve those documents, and then it will take into consider those documents to answer the question. Let's take an example, like line by line what I'm talking about. Like, let's say if your company has some private data, which are like HR policies, salaries, product specs, and stuff like that, right? So an employee asks, what is our leave policy for maternity, right? So it will not be answered based on the LLM will basically not be able to answer this because this data is specific to your company. Now, this is where RAG comes into picture. So what RAG will do is it will take all the internal policy documents of your company, and through this framework, we'll put it into a vector database. Okay. Uh, some of the popular vector databases are Pinecone and FAISS. This is by Facebook. Okay. Now, when a user asks a question, what is the maternity leave policy? First, what it will go is it will go and search the vector databases. Now, the interesting part about vector databases is you can do a semantic search. So normal search that we do is a keyword search, but semantic search is different. Semantic search means if you change the tone, so it's not a word to word matching. Instead, if you change the your wordings also, it will try to get the intent of your question and then do a relevant search. So it's basically semantic search. Vector databases basically help in semantic searching. Now the LLM will first look at the documents based on the user query. It will find the semantic chunks in the vector database and then answer your question. And now that answer will be right because it had the context of your company, right? It has seen the policy documents of your company, and that is how it can now answer this question that employees are eligible for 6 months of maternity leave after completing 1 year of service. So in your company, whenever AI comes in, first thing you will be working on is RAG, which is retrieval augmented generation. So this was RAG. We'll cover this like right now. I'm talking about all of this in a very high level, but we'll go into details into each of these concepts and then talk about it. Now, what are agents? I think, yeah, like Sneha, I think you said, right, your company wants to work on agents. Now, see, agents are nothing like when we use ChatGPT, right, we are basically asking questions, right? We are just doing a Q&A with LLM, right? So what are agents? And some researchers thought, why are we only restricting ourselves to do some Q&A with LLMs? Why not ask them to do some task for us? So agents are nothing but LLMs with hands, which basically means like they can also do the function calling or any other work for you. So agents are basically, they have some tools along with them. So like web search, searching on the web is a tool. Querying database is a particular tool. Calling APIs to check whether stock prices is a tool. Running code like Python scripts or anything. Automating workflows is a tool. So basically, agents are nothing but LLMs which can do certain tasks for you. So they are still LLMs, but now instead of just answering your queries, What they basically do is they do task also for you. So basically, what you do with agents is you give it a goal. Like let's say, book me a flight to Tokyo under 10,000. And what it does next is it will plan, it will call tools to search the flights, compare the prices, call the booking API. After doing each step, it will observe the results and it will then decide that, okay, whether I'm done with the task or not. And if it thinks that now, okay, I'm done with this task, then it will give you the result. So basically, agents are nothing but LLMs running in a loop. So Cursor is the best example of this particular thing, right? So if you ask it to develop a feature, what it will do first is it will read the files, it will edit them, it will run tests and read the error, fixes them and iterates, right? So it's kind of running in a loop and doing a task for you. So agents are nothing but LLMs running in a loop and doing certain tasks for you, right? So they are synonymous to like real world agents where you give a task to them and they do that task for you, right? So here you are giving LLM a task and you are expecting the LLM to complete the task and give you the results. So that is what agents are. Okay. Any questions on this? Okay, I'll take that as a no. Now, okay. Now one more concept which is called as the model context protocol. This is also a very, a buzzword which is used across the industry. It's trending now. It's trending a lot now. So what model context protocol means is, like, let's say if before MCP existed, what used to happen is, like, let's say if you are developing 3 applications in your company, which is like app 1, app 2, and app 3. And you need to get some data from Slack, GitLab, or some database, right? So in order to call the tools of Slack, right, in app 1, you will have to code it out. In order to GitLab, in order to connect to GitLab, you will have to code that in app 1. In order to connect to any, you will code it in app 1. You will code it in app 2. You will code it in app 3 as well. So you will have to do the coding in all the 3 apps basically to get the information. Whereas it could be reusable, right? So I mean, the library could have been the same. So if I know how to connect to Slack from app 1, why not reuse that particular library in app 2 and app 3? Why do I need to code it separately? So that is what MCP is. So it's like an API gateway for tools, right? So what it means is, like, let's say what each of these things will do is, like, what Slack, what GitLab, and this will do is it will tell the MCP server that these are the tools that I can give you access to. This is the structure of the functions that I have. Now, if app 1 wants to connect, get some info from Slack, it will not talk to Slack directly, or I don't have to code that. I will just talk to the MCP server and give a query in a natural language that get me all these messages, and app 1 will be able to do it. I don't have to code all the functionality of connecting to Slack, talking to it, and everything. So you're seeing it over here, right? Like how this model context protocol is making it easier. I don't have to code in in each of the apps. I can just I'll create an MCP server which will have access to all these particular tools. Now I go and talk to the MCP server and tell it, hey, I want to do this in natural language. It will figure out what is the API I need to call, what are the things that I need to manage, and it will do everything for you. So that I don't have to write the code in app 1, app 2, app 3. So that is what MCP servers are on a high level. So basically, let's take an code example of what an MCP server is. Let's say if you had 2 apps, app 1 and app 2, and they want to connect to Slack, right, to do something. So in both the apps, you would typically install the Slack SDK, handle authentication, read Slack API docs, write functions, handle errors. So both apps end up writing this duplicate logic. Then your app decides when to call this, what parameters to pass, how to handle failures, right? Each app becomes responsible for handling Slack, right? After MCP comes in, right, you don't have to go in each and every app and connect this code. What you instead do is you just connect to the MCP client and pass it a query, send a message saying hello team to the general channel, right? So what now you see the difference, right? Instead of coding everything, I'm just connecting to the MCP client and telling it in a natural language that post a message hello team on the general language. Now the MCP client will take care of talking to Slack. It knows that how to talk to Slack, how to authenticate to Slack, what is the API that I need to call behind the scenes to post a message. So all that will be handled by MCP. So the advantage that we'll get via this is that you don't have to code everything over there. Like you don't have to code everything in each and every application. MCP is where everything will be done. You just make a natural language code. So agents are they rely on MCP to talk to any of the external sources. So they are also becoming very famous. Like RAG agents and MCP are like top trending terms today in terms of the AI world. So these were the 10 concepts that I just wanted to explain. I'll share this material also with you, these notes that I have created. You can go back, read, and they will start slowly making sense. These are heavy terms, but I think